This video will cover the fundamentals of using GDB, Valgrind, and perf for debugging and optimizing C++ code. Some of what's shown will be C++ specific, some will be compiled language specific, and some will be language agnostic. It is not meant to be comprehensive. There are many tools and concepts that won't be covered, and those that are covered will only be touched on. It's meant as a starting point that will give you an idea of where to dive deeper. For brevity, the changes I'll be making are planned out, and some parts of the video will be sped up. Debugging and optimization in real life is usually messier and slower than what you'll see here. The program on screen simulates the heat equation, but the particulars of the problem are unimportant since it's just a vehicle for showing debugging and optimization methods. In brief, a two-dimensional grid containing heat values is used to represent the temperature distribution on a rectangular plate. The step function updates the plate, and the goal of the program is to determine how many steps are required for the greatest single iteration change of any cell to drop below a certain value. Compiling and running this program results in a segmentation fault, which happens when a program tries to access memory that it doesn't own. Since I compiled with the -G flag, meaning that the hot plate binary has debug symbols, Valgrind can figure out where in the code the segmentation fault occurred. GDB can give the same information. Launching the program with GDB and running it until the segmentation fault occurs, then getting a backtrace, yields the same information as shown by Valgrind. We should look for the problem on lines 34, 48, and 79. Looking where Valgrind and GDB pointed reveals the problem. Iterating until calls and rows, rather than calls -1 and rows -1, leads to the segmentation fault, since update cell value tries to read from adjacent cells. This is one cell beyond the end of the array on the last iteration over each row and each column, leading to out-of-bounds memory accesses. Fixing this prevents the segmentation fault, but uncovers a new problem. Iteration continues indefinitely. Running with GDB, setting a breakpoint at the end of the step function, and getting a backtrace shows what's wrong. Max change has gone to infinity even though it should never exceed 25 given these initial conditions. Discarding an erroneous plus fixes this, but the simulation is very slow. The first thing to try is compiler optimizations. The program can be sped up significantly for no work on my part by allowing the compiler to try its hand at optimizing. Even so, the program is still slow. Given these initial conditions, an efficient implementation should run almost instantaneously. I'll use perf to record a run of the program, then report where it found slowness. Lots of time is being taken by allocations, freeze, mem moves, and similar. In C++, this is often caused by unnecessary copies. The loops where the computation is happening are the first place to look since that's where most of the work is happening. And indeed, update cell value, which is used thousands of times per step, is copying old plate every time it's called. Passing the grid by const reference instead of by copy leads to a dramatic speedup. Now that the worst of the problems are taken care of, I'll update the initial conditions to allow performance to be accurately measured. If the program completes too quickly, statistical profilers like perf aren't able to collect sufficient data to determine where time is being spent. 20 seconds is more than sufficient. When optimizing, it's important to get an idea of the performance that should be expected. Given this problem and these initial conditions, 4 operations per cell update, about 1 million cell updates per iteration, and 1,800 total iterations, the program could theoretically complete in about half a second on this machine, which has a 4 GHz processor and AVX2. Reducing the program's execution time to under a second should be attainable, even given that a program's performance is affected by more than just the math it does. GDB can be used as a crude statistical profiler given sufficient runtime. Running the program and intermittently interrupting it with Ctrl-C, then printing a backtrace, can give you a decent idea of where a program's time is being spent. Since GDB shows what's expected, that most of the time is being spent in the for loops in the step function, I'll use Valgrind to check for excessive cache misses, which occur frequently in programs with poor memory usage patterns. Since Valgrind's detailed analysis comes at the expense of speed, I'll decrease the problem size before running it. CacheGrind shows a very high L1 cache miss rate, so the program's memory access is clearly not well optimized. This may be due to the incorrect ordering of the for loops, which are structured such that an element of one vector is updated, then an element of a different vector is updated, etc. In order to process data contiguously and thereby decrease cache misses, I'll change the iteration order so that all of the cells in one vector are updated before moving on to the next vector. With these changes, Valgrind reports a lower L1 cache miss rate, and the program's performance has more than doubled. Over half of the program's runtime is now system time. In a program like this, system time should be negligible, so I'll investigate with perf. Mem moves and allocations still take a significant amount of runtime, so I'll get rid of the copy that happens at each step, instead pre-allocating 2 plates and swapping them on each iteration. This speeds up the program by a factor of 4. From here, optimization will give diminishing returns. This is typical. Usually, a few easy changes toward the beginning of the optimization process yield huge dividends, while increasingly troublesome changes later in the process fail to increase speed significantly. Profilers usually can't tell that the algorithm underpinning a program is inefficient, as is the case with a pair of for loops in step. It's more efficient to do all of that work in a single loop, iterating over the grid once rather than twice. This memory optimization, along with other algorithmic optimizations, discarding redundant math and only updating max change when it's below EPS, get the program close to running in 1 second. CacheGrind still reports a high data cache miss rate, so I'll compact the data further by using large single vectors to represent the whole plate rather than vectors of row vectors. This decreases the cache miss rate, but it's still high, and the resultant speedup is trivial at best, so I'll do away with one of the stored plates and instead use 2 buffer rows, nearly halving the program's memory footprint. That significantly decreases the cache miss rate and yields a non-trivial speedup. With all the low-hanging fruit harvested, I'll use perf to see what the compiled code that's doing the heavy lifting looks like. This level of optimization is rarely necessary, but if you need the utmost performance, hand-tuning assembly, or at least checking the assembly that the compiler is generating, can be a good idea. Simple, looping code like this should result in vector instructions, which usually start with the letter V. The most heavily used instructions in this program are not vectorized. I'll tell the compiler to use AVX2 vector instructions, which will work on most modern hardware and allow 4 double precision operations to be executed simultaneously. This results in another speedup, nearing the theoretical performance ceiling. Perf confirms that the most heavily used instructions are now vectorized. Omitting one of the buffer rows is worth trying, since with a little care only one is necessary. This will eliminate the calls to standard copy that take 25% of the program's runtime, which will hopefully squeeze out a bit more performance. When I compile and run again with this change, though, performance decreases. Perf shows that the updated loop code isn't vectorized to the same extent. It turns out that using a single buffer row introduced an inter-iteration dependency, precluding the more extensive vectorization that was possible with 2 buffer rows. This demonstrates an important principle. Assumptions about how a change will affect speed cannot be trusted. Measurement is vital. The program has been corrected and performance has increased by 4 orders of magnitude just by using perf, Valgrind, and GDB in combination with some knowledge of C++ and modern hardware. C++ optimization is a hard-won art, but hopefully this video has given you an idea of where to start and an understanding of what's possible.